In this video, I want to point out some things that we already know about pivot positions in a matrix and consistency of a matrix and how those affect the span of a set of vectors. So I want to do this by talking about a few examples. So let's first start out with an example where we're just computing the span of a single vector. So we're going to find the span of the vector u, whose entries are 1, 1, and -2. So this is the simplest possible situation. And the span of the single vector we'll find is the line through the origin in the direction of the vector u. So if we think about u as a 3x1 matrix, A as a 1x1 matrix, we can think about the matrix equation u multiplied by A is equal to an arbitrary three-dimensional vector whose entries are b1, b2, and b3 as the augmented matrix 1, 1, -2, then b1, b2, b3 in the augmentation column. So we can very easily row reduce this matrix. We can subtract the first row from the second row. Then we can add twice the first row to the third row. And we can see here we have an augmented matrix in reduced row echelon form. It has exactly one pivot. So the vectors b1, b2, and b3, which are in the span of our vector u, are the ones satisfying the two equations b2 minus b1 is 0, and b3 plus 2b1 is 0. Now we can translate these into two equations. B2 is equal to b1, and b3 is negative 2b1. So we can see that the vectors which make this system consistent are exactly the vectors b, whose entries are b1, b2, b3, and satisfy the condition that b2 is equal to b1, b3 is negative 2b1. So we can factor out the b1, and we get b1 multiplied by 1, 1, -2. So we have indeed verified that the span of u, this single vector, is all of the scalar multiples of u, which we know is just a line in R3. So we can see here we have an example where we have exactly one pivot position and the span has exactly one dimension. And just as a little note here, it doesn't actually matter what dimension we're working in. If you choose any integer n that's positive, so say 5 or 10 or 2000, you take a single vector, the span of that single vector will always be a line, and it will lie in that n-dimensional space. So let's try an example with two vectors. So here we have two vectors, 1, 2, 3, and 3, 6, 9. It's pretty easy to see here that v is already a multiple of u. That tells us from our previous example that v is going to lie in the span of u. So if we simply take a vector and we throw another vector in that is in the span of that first vector, we should expect the span to not actually change. So let's just take a look at this algebraically and confirm that our intuition is correct. So we start out with the augmented matrix with u in the first column and v in the second column. Now, we'll take the first row, multiply it by 2, subtract it from the second row, and then we'll take 3 times the first row and subtract it from the third row. And we see again that we end up with a matrix with a single pivot position. So now if we write down the two equations that must be satisfied for this to be consistent, we'll have two equations which characterize the span. The first equation is b minus 2a is 0, and the second equation is c minus 3a is equal to 0. If we solve both of these equations for b in terms of a and c in terms of a, we'll get b equals 2a and c equals 3a. So we can see the vectors which satisfy this equation are going to be the ones with entries a, b, and c, such that b is equal to 2a and c is equal to 3a, which we can think about as the vector a times 1, 2, 3. So just as we claimed, the span of these two vectors is exactly the span of u, or you could also equivalently think about this as the span of v, since we could think about u as being 1/3 v. It doesn't matter, the relationship is totally symmetric here. So for our next example, we're going to use the two three-dimensional vectors e1 and e2. So to do this, we're simply going to write down the augmented matrix with columns e1, e2, and then a third three-dimensional vector. Since we've chosen such simple vectors, our augmented matrix is already in reduced row echelon form, which is very handy because we can simply read off the set of vectors which satisfy this condition. So namely, C must be equal to 0 for this matrix to be consistent. The set of vectors in R3, whose third entry is 0, is simply the xy plane. That is, all of the vectors whose z-coordinate is 0. So you can see here we have two pivot positions, and we get a two-dimensional span. Okay, so this example may seem a little bit silly. So let's try a less trivial example and see what it actually gets us. We're going to take the two vectors u, entries 1, 1, minus 2, and v, entries 0, 2, 1. Again, we set up our augmented matrix. The u is going to be the first column, and v will be our second column. We can subtract the first row from the second row. Then we can add twice the first row to the third row. Next, we can subtract twice the third row from the second row. And finally, we can interchange the second and third rows. Our third row gives us the condition for our matrix to be consistent. Namely, b minus 5a minus 2c must be equal to 0. So now we can use our geometric intuition from the previous example to actually interpret what a linear equation in 3 variables represents. So because there are two pivot positions, the set of vectors a, b, and c, such that negative 5 times the first coordinate a plus b minus 2c is equal to 0, is in fact a plane. So this is a nice way to see that if you take a linear equation in 3 variables, the set of solutions inside of R3 will form a plane. In general, if you take a linear equation in n unknowns, the set of solutions will form an n minus 1 dimensional subspace of Rn. So a linear equation in 2 variables is a line in R2. In 3 variables is a plane in R3. In 4 variables is something that looks like R3 embedded in R4, which is hard to visualize, but it is what it is. In 5 unknowns, again, this is impossible to visualize, but it should be a 4-dimensional space embedded somehow into 5-dimensional space, and so on. So for our last example, let's consider 3 vectors. So we have the vector u with entries 1, 1, minus 2, v with entries 0, 2, 1, and w with entries 1, minus 2, 4. Again, we set up an augmented matrix, and after we do a bunch of rather tedious computations, which I won't subject you to, we get the following reduced row echelon form. So we can see here that our reduced row echelon form for our matrix has 3 pivot positions, 1 in each row. And as we know from the previous chapter, right, so SE3 tells us that if we have a pivot position in every single row, then our linear system is consistent. So whenever this happens, where we have a pivot position in every single row of the coefficient matrix, we know that the linear system is always going to be consistent. So that says the span of these 3 vectors, u, v, and w, will be all of R3, which is another way of saying we can write every single vector that is 3-dimensional as some linear combination of u, v, and w. In fact, this reduced row echelon form, as nasty as it is, tells us exactly how we would do it. So the first weight is going to be given by this expression here. The second weight is going to be given by this expression here. And the third weight is going to be given by this expression highlighted here. So for example, if we wanted to know how to express the vector 15, 15, 15 as a linear combination of u, v, and w, we would simply plug the numbers 15 in for A, 15 in for B, and 15 in for C. So we record our observations here in the following proposition. If v1, v2, down to vn are m-dimensional vectors, then the dimension of the span of v1, v2, down to vn is equal to the number of pivot positions in the matrix whose columns are v1, v2, down to vn. In particular, the span of v1 through vn is equal to Rm if and only if the matrix with columns v1, v2, down to vn has a pivot position in every row. Now, because we know the number of pivot positions in our matrix cannot exceed the number of columns in our matrix, we have the following handy result. If a set of vectors spans Rm, then there must be at least m vectors in that set. And as a word of caution, it's important to remember that the converse of this statement is not true. There are sets of vectors, as we have already seen in the previous examples, that have enough vectors but do not span the space. This is a topic that we will discuss at great length when we move on to linear dependence and linear independence.